In activity 9.3, we're exploring the relationship between work, force, and kinetic energy. Now remember, work is the transfer of energy. So energy is the ability to do work or cause change. When that change happens, we're doing work. Kinetic energy is the energy of motion. So we saw elastic potential energy before. That's energy that's stored in a spring. When we stretch a spring, we do work to stretch it. That energy is stored in the spring. Okay. When something's actually in motion, it has kinetic energy. Kinetic energy is the energy of motion. And increasing something's velocity gives it more energy. So when objects speed up, they gain energy. When objects slow down, they lose energy. And it doesn't matter if we're talking about kinetic energy, potential energy, or work. They're all measured in joules. Now the idea of this lab was to figure out the relationship between kinetic energy and work. Now remember, forces cause accelerations, and if the force and the motion are in the same direction, then the object speeds up. If they're in opposite directions, the object slows down. But regardless, if the net force is not zero, the object accelerates. Now, this went through and said, all right, well, remember, work is equal to force times distance. And if it moves a distance x, that's times the cosine of the angle between them. But if they're moving in the same direction, then the cosine of 0 is equal to 1. So what we can do is we can say work is equal to force times distance when it's just moving, when the force and the motion are in the same direction. And because Newton's second law is net force equals mass times acceleration, we can say the net work done on an object is equal to the net force times the distance it moves, Fx. We're going to go ahead and what we want to do is we want to know how work affects velocity, how work affects kinetic energy, which is how fast something is moving. So instead of using F, we're going to replace that with acceleration. So the net work done on an object is equal to its mass times its acceleration times however far it moved. But remember, acceleration is a change in velocity, and we have the third kinematic equation, which says v squared equals v naught squared plus twice the acceleration times the change in position. Remember, it moved that far, so instead of using delta x, I'm using x. We're going to solve this for acceleration and sub it into that equation. So I'm going to subtract over the initial velocity, so v squared minus v naught squared equals twice the acceleration times however far it moved. Now I'm going to divide off the 2x, divide off 2x, and I get acceleration is equal to the change in the squares of the velocities divided by twice its change in position. I can take that and put it into this equation. So the net work is actually going to be given by mass times x times this v squared minus v naught squared all over 2x. And remember, that's in parentheses. This x is going to cancel that x, so what I'm left with is the net work is equal to, I'm going to go ahead and distribute this mass through, mv squared minus mv naught squared all over 2, and now I can factor out that 1/2, and I get the net work is equal to 1/2 mass times velocity squared minus 1/2 mass times initial velocity squared. This right here is a very powerful tool. In fact, it's so powerful we give it its own name. This term right here is called kinetic energy. It's the energy an object has due to its motion. And what this tells us is the net work done on an object, net work, is equal to change in kinetic energy. So just by knowing how much something's velocity has changed and knowing its mass, we can figure out how much work was done on the object. You'll notice this no longer has to depend on force or acceleration or distance. It is simply a measure of velocity and mass. So the change in kinetic energy, delta Ke, is equal to final kinetic energy, Kef, minus Kei, initial kinetic energy. And that really is just 1/2 mv squared minus 1/2 mv naught squared. This is the work energy theorem. So the net work is the change in kinetic energy.